Hi everyone, this is the notes for lesson 4.2 on similar triangles. So last class we talked about triangles or figures being similar. They had proportional sides and congruent angles. So today we're going to learn 3 shortcuts on how to prove triangles similar without having to show all the sides proportional and all the angles congruent. So this is kind of like what we did in chapter 3, where we had our shortcuts to prove triangles congruent, side, 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 angle, side, and so on. So same idea, but now we're using it for similarity. So we have 3 rules: the angle-angle similarity postulate, the side-angle-side similarity theorem, and the side-side-side similarity theorem. So when you write those out, you can't just write SSS because that would imply congruency from what we learned in chapter 3. You have to put the similarity symbol after all of them, so I would know that you're talking about being similar and not being congruent. So let's look at our first similarity postulate. So it says that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. So this shortcut tells us that all we need to make triangles similar is 2 congruent angles. So as we can see in our example, we have that angle A is congruent to angle D, and angle C is congruent to angle F. So since we have 2 angles congruent, the triangles are similar. So we can write our similarity statement. So triangle ABC is similar to triangle DEF by the angle-angle postulate. Why don't we need the third angle? Why is it sufficient enough to say that we have 2 congruent? Very good, because if we know 2, we know the third angle is also congruent by the third angle postulate, or third angle theorem that we learned in 3.1. So our second method to prove triangles similar is the side-angle-side similarity theorem. So this theorem says that if an angle of one triangle is congruent to an angle of a second triangle, and the sides that include that angle are proportional, then the triangles are similar. So since we have sides in this theorem, we have to check for the proportionality, just like we did from 4.1. So we have to make sure we have our one angle congruent. And we do. We have angle I is congruent to angle L. And then we would check that our sides are proportional. So just like we did last lesson, we would make ratios out of them. So what I did is I took the bigger number, smaller number on the big triangle over the smaller number on the small triangle. I divided by the GCF and got 3/2. Then I took the bigger number, divided by the bigger number in the other triangle, reduced by GCF of 6, and I got 3/2. So since my scale factors are the same for both ratios, we have that the triangles are similar by the side-angle-side similarity theorem. So our last method to show that triangles are similar is the side-side-side similarity theorem. So I know what you're thinking. We got to have 3 sides proportional, and that is exactly correct. So if we take a look at the theorem, it says that if the corresponding sides of 2 triangles are proportional, then the triangles are similar. So we would have to check for this one all 3 sides being proportional, but the shortcut is that we don't have to look for the angles. We don't care about them if we have all 3 sides proportional. So in our diagram, we would compare just like we did from 3.1. So I looked for the smallest in the big one, the smallest in the small one, and I reduced. And then I looked for, well, I'm going to skip the biggest, and then the biggest, and I reduced. And then if we look for our leftovers, that would be 30 over 15, and I reduce. So since I got 2 for all of them, we know that the triangles are similar. So triangle MPN is similar to triangle QSR by the side-side-side similarity theorem. So that value we found was 2 for our scale factor. So remember, that would be what we multiply to the small one to get to the big one, what would you need to multiply the big one by to turn it into the small one? Very good, 1/2. It's the reciprocal of the scale factor you already have. So to get to the big one, multiply by 2. To get to the small one, multiply by 1/2. So let's look at some examples. So we're trying to see if the triangles that we have are similar. So we're going to look for either having two angles congruent, having one angle and two sides where the sides are proportional, or having three sides proportional. So you have to check that the sides are actually proportional. You can't just look at them and say, yep, those triangles are similar. You have to make the proportions. So it asks us to determine if the triangles are similar. So tell how we can prove it. So that would be one of the three reasons at the top. Write our similarity statement. And if we can, find the similarity ratio, which is also known as the scale factor. So if we take a look at our first picture, we can see that we have angle A and angle I congruent. So that's one angle. Since we do not have any side measurements here, we know that it's not going to be side angle side or side 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 similarity. It's going to have to be angle angle if we have that those triangles are similar. So is there anything hidden? Very good. We got hidden congruent vertical angles. So that is our second angle. So are the triangles similar? Yes, they are. I'm just going to write our angle that we know. So angle PGI is similar or congruent. Angles are congruent, not similar. Congruent to angle BGA. So since we know that the triangles are similar, we can write our similarity statement. So triangle PIG is similar to triangle BAG by the angle-angle similarity postulate. So again, to check similarity, we look for our three shortcuts. Two angles, two sides proportional in an angle, or three sides proportional. So the next example is one that they like to use a lot because it kind of looks confusing, but it would be a lot easier if you could separate those two triangles. So if you can see it, we have this little triangle that's kind of sitting right inside the big triangle. So one helpful thing to do with these is to draw the two triangles separately. So, you know, my drawings are never to scale, so that part doesn't matter as long as you label everything right. So that's my bigger one, and here's my small one. So I drew them exactly how this one was turned to make it easier to see what goes together. So I know at my right angle I have an A, and my bigger one, the bottom vertex is an E, and then this right vertex is a C. And the smaller one, the bottom vertex is a W, and the right one is an L. So then we have on the big one, this whole side would be both pieces together. So 6 plus 6. What's AC? How big is AC? Good, I hope we got 16. So in the little one, we don't have to do any adding because this is the side of the little one. So 6 and 8. So just by looking at it, what do you think is our reason that we're going to use to prove that these two triangles are similar? Good, we have an angle, and then we have the two sides that form that angle. So we would have side, angle, side, as long as those sides are proportional. If they're not, those triangles are actually not similar, even if we have what looks like side, angle, side. So I'm just going to list that angle A is congruent to angle A because of the reflexive property. So now I'm going to make my ratios. So smaller side in the big triangle is 12 over the smaller side in the small triangle, 6. And divide those and I get 2. The bigger side is 16 over the bigger side in the small one is 8. Divide those and I get 2. So since those are the same, we know that our triangles are similar. That's our similarity ratio or scale factor, as we called it last lesson. So I can write my similarity statement and say that triangle AEC is similar to triangle AWL by the side angle side similarity theorem. Very good. So I would like you to pause your video and check the other two. So remember, you're looking for side angle side with proportional sides, angle angle with two congruent angles, or side 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 with three proportional sides. So go ahead and pause and try those other two examples. So looking at the example on the left, let me zoom in a little bit. Even though we had a congruent angle and it kind of looked like we had those proportional sides, we didn't actually have proportional sides, because if we match up the smaller with the smaller, 16/9 can't reduce. And then if we match the bigger and the bigger, that one can reduce, but not to the same number we had up there. So since those are not equal, we do not have similar triangles. So be careful and don't be tricked. Even though they show a side angle side, you might not have similar triangles like we did here. So triangle RAD is not similar to triangle WIN. So RAD is not similar to WIN. So the next example, we can do the same thing. So if we look at the pictures, we have three sides and three sides. So I would think side, side, side. But we have to check, are all the sides proportional? So smaller side to smaller side, we get 3/4. Bigger side to bigger side, we get 3/4. We don't have to check the third side since they're isosceles. We know that they're going to be the same ratio. So we would have the triangle ABC is similar to triangle EFG by the side, side, side similarity theorem. And our scale factor is 3/4. So let's take a look at our proofs. So we're going to do 2 in this video, and then I'll make another video for the ones that are a little bit longer. So first, we're going to start with this one. Okay, so they tell us that, or given, is that MA over HT is equal to AD over AT. So what are they trying to get us to realize by saying MA over HA is equal to AD over AT? Well, what does this look like right here? What is it when we have two fractions equal to each other? Very good, it's a proportion. So that means that those sides are proportional. So since they didn't give us a third side, we know it's not side, side, side similarity. But we do have something that's hidden. So if we check for our hiddens, we have those congruent vertical angles. So how are these two triangles similar? Good, side, angle, side, similarity. So we're still going to do a checklist, sort of, because our sides are actually going to be in one step, and then we'll show our angle. So our sides are given to us, so MA over HA equals AD over AT. So remember, that shows us our proportionality for our sides. And we know that that's true because it's given. So we did our sides. The next thing is our angle, and we have our congruent vertical angles. So angle MAD is congruent to angle HAT because vertical angle theorem. Remember, that tells us that all vertical angles are congruent. So we've showed everything on our checklist, so that means that triangle MAD is similar to triangle HAT. So we got MAD HAT by the side angle side similarity theorem. Very good. So let's take a look at the bottom one. So they gave us parallel lines this time. OT is parallel to UV. So remember, when you see parallel lines in triangles, think congruent angles. Parallel lines means congruent angles. So I know we're used to using alternate interior angles, but in this picture, it's not alternate interior. We don't have our Z. Remember, we look for our Z? We don't have it, but we have transversal right here with these parallel lines. So we have these two angles. What kind of angles are those? Corresponding angles are congruent here because we have those parallel lines. So we have corresponding angles on that side and on this side. Or if you wanted to, you can use that angle L is congruent to itself because of the reflexive property, which might be easier because it's easier to name that angle than this angle. Okay, so I'm going to start with that line OT is parallel to line UV because it's given. And from that, we figured out that we have those congruent corresponding angles. So angle LOT is congruent to angle, I'm just going to call it U because there's nothing adjacent, because of the corresponding angle theorem. So for our checklist angle, we got one angle. So our second angle, again, you can use these two, or you can use that one. I'm going to use angle L is congruent to angle L because of the reflexive property. So there's our second angle. So we have that triangle LOT is similar to triangle LUV because of the angle-angle similarity postulate. So if you would like, I'm sorry, you couldn't see that. If you would like to watch the other proofs, which you should, check the other video. Thanks. Warner out.